first thermodynamic laws. We have several examples, which I would like to leave them for your homework, but I don't think we have time to go through all the examples. Okay. So you need to do it as your homework. And if we have time, we can go back to take a look. But now we need to move to another topic, fluid. Okay. Gas and liquid, they can flow, so they call the fluid. Fluid is a substance can flow. For the fluid, compared with the solid, it has many different properties. Okay. First, let's look at the pressure inside of the fluid. And to find the pressure inside of the fluid, we can do the force analysis. And if we try to do the force analysis for the fluid, there is some good thing is that you can choose any appropriate part inside of the fluid to do the force analysis. So for fluid in static equilibrium, so that means it's not there's no flow inside of the fluid. Okay, that's a fluid in equilibrium. Any arbitrary portion of the fluid is in static equilibrium, and we can choose an appropriate portion to draw free body diagram. So now let's look at this case. You have some fluid inside of the container, and if you choose an arbitrary part, this one, okay, to do the force analysis. So you can see there are you can consider the force acted on this along y direction. So how many force do you have? You have the weight of this part of fluid. Okay. So that's mg. For the mass for this part is m, and the height here is considered is h. Okay. And the cross-sectional area here, we call it A. So we can choose any arbitrary part. Here, H and A are arbitrary quantity. So it has a weight, mg. And it also has some pressure at the top surface. That's a pressure from the atmosphere. Okay. We call this F naught. From the pressure, atmospheric pressure, which is A multiplied by A, right? Force equals to the pressure multiplied by the cross-sectional area. Okay? On the other hand, you have some force here. So this is the force acted here. And you also have some force from the pressure, upward pressure. Okay? From the rest part of the fluid. We call this F equals to pressure multiplied by A. Also, right? Force equals to the pressure multiplied by the cross-sectional area. Here, the cross-sectional area is also A. Any question here? That's a force analysis. The three forces together should give you 0, right? Why?
Because it's in equilibrium.
It's not moving in the equilibrium. So all the forces together will give you 0. So you should have mg okay, plus F equals to F naught. Right? The three forces should cancel each other. Oh, sorry.
No, yeah, wait a second.
Is it?
No.
No.
Yeah.
This is downward force. This is upward force, downward, downward. So it's let's make a positive like this. So it's mg minus
No, it's minus mg.
F.
plus f minus f naught equals to 0. So it's f naught equals to mg plus.
I think the mg is negative too. Mg is negative, right?
Yes.
Negative.
There you go.
No.
Yes.
Yeah.
That's right.
Okay.
Just look.
Negative, positive, negative. Okay. So, and then let's rewrite these quantities. This one is P multiplied by A. This one is P naught multiplied by A. Okay. Now, how about mg? The mass m equals to the density multiplied by the volume, right? Mass equals to the density multiplied by the volume. And the volume can be written as the height multiplied by the cross-sectional area, right? Okay. So then this one can be written as negative rho HAG equals to 0. And the cross-sectional area A can cancel for every term. So finally we get this. P equals to P naught plus rho HG. Okay, so this is a general expression for the pressure dependence on the height, on the depth, okay, in the fluid. So this is the pressure and the depth of H. It depends on the surface pressure, P naught. It depends on the height measured from the surface. It also depends on the density of the fluid. Okay. And this G is a constant. So this is just the surface pressure plus the pressure introduced by the height here. So from this expression, we can see a few facts. It depends on the pressure, right? So if you have 2 cups of water, one is placed in the normal air, okay? Another is placed in the vacuum. So for the same height H here, so if you can get pressure here and pressure here, this is air, this is vacuum. For the same height H, do you have the same pressure or different pressure? Which one is larger and different?
The air is larger.
So the pressure here is larger because that's the pressure from this part plus the air pressure here and the surface. But if you place it here like this way, you don't have pressure and the surface. So this is 0 plus rho GH. This one is P naught plus rho GH. Okay. And the dependence on the density. If you have a cup of water and a cup of say oil, so at the same height depth measured from the surface, which one has a larger pressure? Okay, so I'm saying if you have, this is water, this is oil, this is air, same height H, and this point, which one has larger pressure? Water or oil?
Water.
Water, okay. they have the same surface pressure, air pressure, but this one is calculated from the density of oil. This one is calculated from the density of the water, and the density of the oil is smaller than the density of water, right? So this is larger. Okay. And of course, in the same curve, so if you compare here and here, point 1 and point 2, which one has a larger pressure? Point 2, okay? It depends on the depth. And that's why you need, okay, dive. You cannot dive too much without, too deep without a very strong container, okay? Free body diving, you cannot reach very deep, okay? Otherwise it will be very dangerous. And even for those submarine, they have to be made with very strong material, okay? Because the pressure is huge and very deep water, okay? So deep water exploring is kind of difficult due to the huge pressure we have, okay? So that's pressure in the fluid. It basically depends on the surface pressure, density, and the depth. Okay.